Okay, welcome to this session. My name is Thais, and together with Davide, we are from the Technical University of Vienna, from the Remote Sensing Research Unit. And will also present remotely, and he's from UDC. We will present about cloud-based EO processing, also with the use case of doing flood mapping with Dask. Can you go to the next one, please? I can do it. You don't need to do it. So for the agenda today, we'll start with Dask and then cloud computing at UDC, go to Stack, then go through our use case and finalize with the Tailwind flood mapping algorithm. Start with Dask. Yeah, so at our department, we mostly work with Python and using these very common libraries like NumPy, Pandas, and XArray. They are very powerful to analyze data in general, but they struggle when handling big data. So if you have big data sets, you probably will fail into this memory error. And this is often the case with Earth observation data, since we work with big data sets. And so the solution we found for that was to use Dask. Dask allows you to even work in your own machine to handle these big data sets, or if you want to work with distributed computation or in the cloud, all possible. But even on your own machine, if you have a big data set and you are facing this memory error, maybe Dask can be a solution for you. What Dask does, it breaks the data into small pieces that we call chunks and process them in a way that they fit in memory. So this way we avoid the memory error. For example, here we want to sum numbers from 1 to 16. Very simple example. So what Dask would do is group it to groups of 4 numbers and then computes the parser result first, and then later computes the aggregated sum to get it. Dask only not do only that. Dask also organize the tasks that you need to be performed. So you can pass to Dask many tasks, and then Dask will create a graph trying to optimize the best way of doing these functions. And to illustrate this would be the graph from this simple sum function. And you can also use Dask for distributed computation, as I mentioned, which I will explain in the next slides. A good point of Dask is that it's written in Python, so if your code is already in Python, it's very easy to use Dask in the end. And Dask has equivalents of NumPy array, of Pandas data phrase. And if we have here, for example, this big Dask array, each one of the chunks will work as a NumPy array, and you can compute tasks. The task will be computed independently in each one of the chunks, and then Dask will only communicate the results when needed. So you also don't have wasting communication costs. Can you go to the next one, please? Okay. As I showed in the first slide about the simple graph, it can be very complex. This one on the left is for simply counting words and then printing them. The one on the right is you have several functions in a row. So just for you to have an idea how this task graph works. And next one. Okay. About the distributed computation, interesting point in here is when you want to work in the cloud or you want to work with several machines. Dask ensures fault tolerance. So if you have a task that fails, Dask will try to rerun it many times. If you have a worker that fails, the other workers will replace it. And also Dask allows adaptive scaling in a sense that you don't need to define the exact number of workers. You can just define a range, and Dask will try to find the optimal number depending on the stage of your process. Next one. Yeah, just some more considerations. Since it's very close to Python, you can, on your machine, you can simply install with pipe install or conda. It's a very secure framework. It's used by companies with very sensitive data like banks. And it's also an open source framework. And it is compatible with the major cloud compute platforms like AWS, Azure, Google Cloud Platform. And Dask also makes a dashboard available so you can follow lively how the computation is going. And in the afternoon session, I will show you how this dashboard looks like. And now we will talk about, you can go to the next one.
Okay.
Yes, go ahead.
Yeah, can you hear me well?
Yes.
If I turn on my camera, can you then also see me? But yeah, if you can hear me, then that's fine. That's just fine. Okay. Yeah, my name is Tobias. I work with EUDC, which is the abbreviation for Earth Observation Data Center. We are a company based in Vienna and also closely connected to TU Vienna. And yeah, you might have seen already some presentations already in the morning. I saw on the schedule that also representatives from Pangeo and so on have been presenting some stuff. And yeah, this fits perfectly, or our presentation will also fit perfectly into this whole environment, because we are, as you just heard, we are using Dask to separate task load to our workers. So we as a company, we offer Dask as a service. And that means that users can launch a Dask cluster without the requirements of having a direct access to cloud infrastructure. So usually in Earth observation, you're needing a lot of or huge load of data, and obviously cannot use your local PC to process all this. And is where cloud infrastructure comes into place, and also the software library, what we are using and presenting here. The ultimate goal is that the users have a low entrance barrier to add or to create workflows and then run it on a huge cloud infrastructure, and then process the results they require. You can do you can run large scale data analysis and in a scalable environment. So how it is set up at EUDC, there is one thing that is called gateway, and this is basically, the name suggests, the gateway to task clusters. So you need an EUDC account, so an account to authenticate with our services, and with this you can create task clusters for your processing. How to or what we thought make it also easier is to provide additionally to that a Jupyter Hub environment. So with Jupyter Hub, you have an existing and configured Python environment where all the libraries are installed. If you need some more libraries, you can directly install it in your Jupyter Hub instance. And the only thing you need is a stable internet connection and a local PC and your laptop and a web browser. And this again reduces the burden with installation and the maintenance tasks of your Python environment. So if you already know libraries you need to have, you can log into the Jupyter Hub, install your libraries, and then use the Dask cluster using the Dask gateway. But you might be interested in the animation. There it is. So you might be asking yourself, okay, where is now the data? Because you're talking about large data sets, so where it is located right now. And there is where Stack comes into place. So as I heard, Stack was already covered in previous presentations, but I will go over it in a short time. So why do we want to use Stack? Again, Stack is spatial temporal catalogs, and it is basically a network of JSON objects. And JSON objects are very easy to use. It is widely used in the whole community to represent data or represent metadata, so to say. So it's straightforward to use it. You have the web compatibility with web standards and wide variety of clients can already read JSON, and yeah, it is just widely used, and therefore its Stack is compatible and interoperable. So the concept of Stack is that you have different kind of entities. So at the top level, you have basically the Stack catalog, which providers can run. And in the Stack catalog, you can add Stack collections. So a Stack collection is, as the name suggests, a collection of items which share the same metadata on a collection level. So on the left side, you can see that we have, for instance, a Sentinel-1 GRD collection. And then one item of this GRD collection represents one Sentinel-1 scene, for instance. The same idea is valid also for the global flood monitoring collection, where UDC acts as a producer of the dataset. And there we have one Stack item per tile, and but all the items share the same base data. And in the item, you then can describe a Stack asset. And an asset is basically a link to a file or a link to the data, basically. So one Stack item of Sentinel-1 GRD has then, as an example, one Stack asset, which is the VV polarization, and a second asset, which is the VH polarization. And then you can, for instance, add a third Stack asset, which might be the XML file or the zip file or whatever fits in your catalog. And those Stack assets are basically then the links to the data. So to sum up a little bit, Stack or one important note is that Stack is not there for the data access itself. because it is very extensible and very to cause the interoperability, very hard to say. Stack is only here for make the data visible or make the data queryable and findable. And for Stack, it doesn't matter where the data is lying. And this is the of Stack, because then you do not need to have all the data stored in one data center. You can create a Stack catalog, but say, okay, this collection is stored maybe at the Copernicus data space ecosystem. The second collection is maybe stored in some S3 buckets in a different company or entity or whatever. But you can find the data all you need in one Stack catalog or in a variety of Stack catalog. Yeah, so Stack provides us with links to the assets, and those assets can live wherever. So in our case, we have, of course, a huge data repository also at EUDC, but we also have some Stack collections, or at least links to, for instance, the metadata of Copernicus database ecosystem. On the drawing on the right side, you can also see again the power of Stack API. So it Stack provides you with a Stack API, and since it is JSON based, there is already a lot or wide variety of clients. So there is the Stack browser you might be familiar with. There is also a QGIS plugin which can read and interact with Stack API, and of course with a variety of Python libraries like the PyStack client library. So at EUDC, this is then the full picture. So a user A needs to authenticate with a user, or needs to create or register EUDC. Then this user can have access to the Jupyter Hub, and then from the Jupyter Hub you can also then have a direct access to the Dask cluster or to the Dask gateway. But the user can also, using, for instance, a Stack browser or a web browser, can directly see what kind of Stack collection we offer, and those Stack collections or those Stack items basically have then a reference to the data which is saved or stored at our storage endpoint. Yeah, and how this will, or if you want to see this in action, in the 1.5 hour is this workshop from that. And yeah, we're happy to want to follow it and see all the processes and the cloud commitment on at UDT together with TUVIN in action. And there are we uploaded recently 2 webinars where we explain how to interact with Stack, and also how to interact with our data processing services. And also there is a documentation page as well. Okay, that is then everything from my side, and I will pass on to Davide.
Yes, thank you, Tobias. So I will start now by giving you a little bit of scientific, let's say more scientific framework in what is Sentinel-1 SAR, what is synthetic aperture radar, and now it can be useful for delineating water bodies, and we will dig in more into this stuff later on in the hands-on lab. So can you go next? Yeah, next. So I would like to ask you, who is familiar with Sentinel-1? Have you ever heard about Sentinel-1? Yeah, okay. I think it's quite popular, I guess. So yeah, here, can you start the animation, Tobias?
I already started it. I don't know if it's working.
Okay. Well, here it's so maybe most of you are familiar with this animation since you know Sentinel-1, but yeah, it's supposed to be nice to see these satellites orbiting around the Earth and give you a little bit of understanding of, let's say, the capabilities and the characteristic of the Sentinel-1 constellation. So we can start by saying that it all started with launch of Sentinel-1A 2014, and the cool thing is that still ongoing, it's still operating. Sentinel-1B was launched, was following Sentinel-1A 2016, but unfortunately there was a failure in 2021, and therefore it's not more usable. But the good news is that we still have the Spain satellite constellation since Sentinel-1C was launched in December, if I'm not wrong, December 2024. And yeah, it's ongoing, it's present. And since May of this year, the calibration phase ended, so all the data are available and ready to be used at Copernicus data ecosystem. And Sentinel-1D will be added to the satellite constellation soon. So the last pieces of information you can find online talks about 2025 as the next launching date. Apart from that, we can say that if you consider the satellite constellation as a two satellite constellation like at present, the fixed orbit separation is about 180 degrees, and we have a 12-day repeat cycle, which grant us around also 175 locally distinct relative orbits. And yeah, basically we get to cover the entire world thanks to this satellite constellation. But what I would like to stress on today, like as an important aspect of this, of this mission, and also that's why the name, the title, "A Game Changer for Other Data," is that Sentinel-1 was really kind of the first mission paving the way to an acquisition plan that is consistent and allows us to do to have a range of benefits and therefore a lot of applications. For starting for interferometry, but not only, we can retrieve soil moisture and water surfaces, vegetation, land cover. And by the way, this is all stuff that also we take care of at TOBN apart from interferometry. So next, please. So it becomes quite straightforward when you have a global acquisition plan that is consistent, at least over land, because this is where we are operating at TOBN. It becomes quite straightforward to also create global backscatter maps like this one, for example, that we did released in 2021 and encompass 2 years of Sentinel-1 images that were acquired at interferometric wide SWOT mode. And as you could see, it was a kind of a tremendous effort because, also processing all this kind of data and aggregating them together for the world globe, encompassed more than or around 5.5 million of Sentinel-1 images, at least for just these 2 years, 2016, 2017. So this gives you also another, let's say, hint on the amounts of volume that we have to deal with when dealing with satellite imageries. Also, something important here to maybe to pinpoint and is that these data that are freely available, by the way, are both available in two channels, which are VV and VH. I don't know if you're really familiar with the channels of Sentinel-1. But anyway, also it's very important to say that at least for these global composite, everything is normalized to a single incidence angle, which is 38 degrees. Because as you might recall, Sentinel-1 or in general SAR system have a side-looking viewing acquisition strategy, which means that we have to take into account of the incidence angle when interpreting backscatter data. Also, this is another term that I hope you're also quite familiar with it. If not, just ask me. But with backscatter, we use this term to basically say what is. We use this word to indicate the signal that is bounced back from a SAR system and that we record. So in this case, we use sigma naught backscatter. Next, please. Yeah, so here in this image, for example, you see an example of Riga from the Sentinel-1 backscatter model that I showed you before. So something that is important, of course, to take away as a message. It's not only that Sentinel-1 is a C-band system, so we have a wavelength of around 5 centimeters, so the signal that we use. But also it's very relevant to see, and it's quite exemplary here, that SAR is really sensible to the electrical properties of water. So we have a strong contrast compared to dry surfaces. So land and water are quite really different from a SAR point of view. Another key point is that what we use also for as the main mode or the main mode operating over land is interferometric wide swath, which again brings me back to the last point. So we have a consistent acquisition plan with a consistent mode, and these really ensure operation in the application that we can leverage from Sentinel-1. Because if we have different modes of acquisition and a non-consistent strategy of acquisition, then it becomes difficult to build up algorithms that can rely on Sentinel-1 or in general to satellite. Yeah. Yeah. It's this is the median. So the median value. In this case, it's VV. Yeah, exactly. VV. Also, maybe this is another point. VV is the preferred polarization channel that we use, especially for flood mapping. At least us at UVM. Other people or other research might leverage also or have leverage also on the VH. But based on our experience, VV offers the best contrast between water and land. And also, it's important to know that this is the nominal resolution, 5 meters per 20 meters for Sentinel-1. And we have an acquisition plan over Europe that brings us like an acquisition frequency of between 1.5 days in the upper latitudes to 4 to 0.5 days in the lower latitudes. And worldwide, we have something between 3 and 12 days, depending on the place of Earth in the, where we are ourselves in the Earth. Next, please. So yeah, once again, it's important also to underline that since we're talking about flood mapping with SAR, the unique characteristic of Sentinel-1 or SAR system is that active microwave sensors are operating day and night and in all weather conditions, so they can penetrate clouds. And that's a very important thing when dealing especially with flood mappings, because compared to other systems like optical system, you might have recalled Sentinel-2, we have this problem of cloud covers that especially when we have a storm or intense rainfall that causes floods, of course, hinders our visibility. That's why Sentinel-1 becomes really important in these cases. And here it's a very intuitive scheme on how backscatter value is different between land and water. So we have a rough surface over land normally, which would create a diffuse backscattering, which would result in a high backscatter value in general. That's why we are seeing higher backscatter values here over land, especially these bright areas. Where we have water, we have a specular scattering, which means the signal is not really bounced back to our sensor. That's why we don't record much energy. Therefore, we have a low backscatter. So that's let's say, the baseline. And of course, based on this observation, it's really intuitive to understand that when we have a flood, so water that is covering up land, basically there is a drop of backscatter, and this is what we want to see at. So we are looking for significant reduction in the SAR signal. And based on our experience, normally the backscatter coefficients decrease by approximately minus 18 decibels. So decibels, maybe just to be clear, decibels is a logarithmic ratio. So basically backscatter is actually unitless, but we use decibels to, let's say, to measure backscatter. And here, here we have, I think it's pretty intuitive from these SAR images on the left. What happens here that there was a severe flooding in Queensland in Australia, and these pretty dark areas are quite easy to spot, and these are the areas that were affected by floodings and floodwater. Next, please. So here we go through, we will go through what is the data cube system that we use at UVN, and which is, let's say, the framework and the baseline for all our operations, like flood mapping and soil moisture retrievals mainly. So next, please. So here we can say a few things, of course, that when dealing with Sentinel-1 processing, especially pre-processing, which is an important step before making Sentinel-1 images analysis ready, is that we need quite some high computing power to run quite some operations that are needed to make Sentinel-1 images usable, so to bring them from level 1 to level 2. So we start normally our Sentinel-1 level 1 pre-processing, at least until the end. We start from a collection from UDC and 30 meters Copernicus DEM, digital elevation model. And we use a Python wrapper that wrap around a GPT graph from Snap. So Snap is the ESA official, let's say, software for pre-processing also, and not only. So here you see a bunch of operation. I will not go too much into details, but yeah, I just would like to the takeaway message could be that there are quite some steps that needed to be make Sentinel-1 usable, and it's just needed. It's just a must, let's say. And what is interesting is that the output, so the level 2 Sentinel-1 image, normally for us is resampled at 20 meters, and because for us 20, so nominally we could also use 10 meters, but SAR is also affected by speckle, which is this phenomenon that makes the typical salt and pepper visuals of Sentinel-1 images. So a good compromise between resolution and precision, and for us is to go to 20 meters. And the output is registered as a stack item. So, and normally we use cloud optimized geotiffs containing encoded decibel values. And here you see it's normally integer 16 with a escape factor of 0.1. So these are metadata that you can find in the stack item. Also, we will talk about the fact that we use Equi7 grid tile system, which is an in-house developed tiling system. And we can go to the next slide maybe for that. Yeah, sure. Sorry? Yeah, so it's a pre-processing operation of Sentinel-1. So you want to, sorry, what? I didn't understand you want to know exactly, yeah. 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 So it's a pre-processing step that is embedded in our GPT graph, and it's about the filling between the slides in the images of Sentinel-1. So yeah, we can, what we can talk about more the details later. So yeah, so based on so this is also an overview of how we deal with our processing in our DataCube system. So there is a part that is online processing. Whenever we receive a new Sentinel-1 images, we run this pre-processing scheme that I was showing you before. We use a tailored algorithm for depending on the application, so maybe soil moisture or retrieval of vegetation or water surfaces, for example. And then we obtain a level 2 product from and on the background we use so there are offline processed data that we use also to calibrate, for example, our algorithm. Yeah, and mostly they are Sentinel-1 modeled parameters. And normally our services run at a global scale and near real time and yeah, freely accessible. So next one, please. This is just an overview of our DataCube architecture. So Equi7 grid, as I told you before, it's our tiling scheme that we are using to easily retrieve time series of Sentinel-1 data. So it's an in-house developed tiling scheme that is especially tailored for land application. And the main thing is that it's divided in 7 bigger zones to reduce the geometric distortions that normally you would have when using let's say a system that covers the whole world. So yeah, you can find the reference here, and also it's open and free to use these Equi7 grid, and you can find also the APSG codes directly in QJS. They're already released from, I don't remember, but I think from the last 2 versions, the APSG codes for all the continents are there, so ready to be used. Next one. And yeah, this is just a little overview of the logic of the Equi7 grid. But yeah, I guess if you want to know more, we can dig in more later, or yeah, you can find the reference code GitHub. Yeah, so next one. So here we go. We will, I will give you a little overview of how we do our flood mapping activities. So the algorithm that we are using at QVN. Next. So basically, it's a rather simple system. It's the output of the flood mapping in the Tubian algorithm is a binary classification into flood, no flood. The main thing is that it's based on bias decision from a priori probabilities. And it's important also to know that at the end, on top of flood and no flood, we also have a specific likelihood value associated to the decision of each pixel. Also, it's worth noting that this algorithm is used in near real-time operation within the Copernicus Emergency Management Service, especially in the so-called Global Flood Monitoring Service. So here you can see how it works basically. A little overview. We have a part that is, as I just showed you before, it's offline. So we have parameter retrievals. So we perform an harmonic analysis of time series over the globe, a water body sampling that gave us then a water distribution that is a model available for, then it's generalized for all the world. We will see that more in detail later. And basically, yeah, from this offline part, we then, From this offline part, we go to the online part where we actually do the Bayesian decision of flood from each incoming Sentinel-1 image. We apply a no sensitivity masking at the end and the post-processing, and then at the end we arrive to a flood classification map. Yeah, so it's basically this method is based on a flood model and a no-flood model. The flood model is a linear model from water body samples. The no-flood model is based on the harmonic time series analysis of the backscatter behavior all over the world for different time of the years. Next one. So basically here it's really easy to understand how it works, the method. So here you could see the scatter harmonic model that we have computed for each pixel for the whole world, and it's modeled for 3 years. So we basically know what is the average behavior of the backscatter based on the time of the year and on the specific place. So these can help us understanding what is the local source signal normally and what is its fluctuation during seasonality, which is important because at least it constitutes the framework of our method to understand whether we have an outlier, for example, when we have a flood, and indeed the behavior of the backscatter goes much further away from the usual behavior. And in this case, if it drops down, as I told you before, we have water, we have low backscatter. If it drops down under a certain level, we know that this is flood. So basically, we compute a no flow distribution and a flow distribution. And here you see the two distribution, for example, that are showcased. And now we compute the probabilities with the Bayesian method, and we associate the decision of whether it's flood or not flood a certain thing. So in this case, you can see 0.2 for flood distribution. Actually, it's the reverse, should be the reverse, but anyway, imagine this, we have a 0.2 for land and 0.8 for flood. So in this case, we have 80% probability of being flood and 20% of being land. So of course, we choose this as our final decision. Next one. Here it's just an impression of how it looks, the non-flood backscatter probability, so the harmonic model. And we have of the same area, an image, the expected value from the Sentinel-1 harmonic model computed for the same area in January, April, July, and October. As you could see, this area is varying. the backscatter value is varying depending on the time of the year, which is normal because maybe you have more dry land, more precipitation in average during a certain season. So we have to take into account that before modeling, before deciding whether this is flood or not flood a certain pixel, or at least this is our method. Next one. And this is the example of how we computed the flood backscatter probability distribution. So we expertly manually collected pixels all over the world about of water surfaces, averaged monthly and per different orbits, and with a global uniform distribution. And then we model, we put in correlation what is the backscatter compared to the incidence angle, which is something that is very peculiar of SAR. You might know that. So as you could see, there is a very strong linear relation between backscatter and incidence angle. So we derived this linear fit model. Now we know exactly what should look like or what should be the value of water all over the world based on different incidence angles. And this is also the standard deviation for each of the 0.5 degrees incidence angle beams, which is pretty stable, around 2.5. Next one. And that's an example. So we are in Greece, 2018 Thessaly flood, and here you have, for example, you see the Sentinel-1 observation during the flood. So you see pretty much a huge contrast between land and between what is flooded water. This is the average behavior from the harmonic model. As you can see, averagely, of course, the situation. And then this is Sentinel-1 flood posterior probability. So the decision made with the Bayesian method. And yeah, and that's the final output. So the delineation of the flood on top of, in the background, you have the Sentinel-2 image, just as a reference. Yeah, next, please. That's another example. We are in Germany for this huge flood that happened in 2021 near Erlangen, Bavaria. So that's the Sentinel-2 image as a reference of the area. Next, please. So this is the SAR point of view from the harmonic model. So this is the average, let's say, backscatter value for 2021, 11 of July. Next one. This is the actual observation, SAR observation for the day where we had the flood recorded. And you can see the contrast again. It's pretty neat, and is going around following the river. So it actually makes sense intuitively that this is flood water. Next, please. That's the retrieval with the TUV flood mapping. And yeah, and next, please. Yeah, so this is the same image as before, and we are opening an important, let's say, discussion about taking into account which are also the problem of SAR images, SAR imaging, and taking into account the flood mapping activities is important. So knowing a priori where flood cannot happen, of course, on very steep mountain slopes, you can already say that flood is really likely not to happen there. So we can exclude that. And also there are really important some important problems that we have to take into account with SAR, which is areas that are low backscatter permanently. So areas that are not water, but the surface exhibit low backscatter characteristics, and which makes really difficult for us to understand whether a flood can happen in there. So we have to be honest about that and discriminate from the beginning in order to don't just give out false information. And just is important to say, here we cannot predict anything. And that's, for example, the case of sand surfaces. if you take a look at Sentinel-1 over, for example, Sahara Desert, it looks like completely dark and black, like water surface, more or less. So, of course, it's really impossible for us to make a prediction. And also there are other important aspects like radar shadows. So since the side-looking geometry of Sentinel-1 impede us to see, let's say, how to say, if we have a really high morphological obstacle, of course, the side-looking geometry of Sentinel-1 impede us to see behind, let's say, this obstacle, and then it's important to flag that as radar shadow. And yeah, and also we have, for the same reason, we have also topographic distortion. So the backscatter value on a topographically distorted surface, it's really difficult to handle. So we have also to be fair about that and discriminate these areas. And last, there is a post-processing also at the end that we do to take into account speckle. We will see that in the workshop also later. What does it mean? It's a really easy mathematical operation, but it helps us to get rid of these really few little pixels that are like, you know, salt and pepper, and that gives us a wrong information. Next. Yeah, and also there are other points that we touch also later that are inherently tied to the Bayesian method. So when we have conflicting distribution, as I told you before, areas that are permanently low backscatter, this becomes really difficult for us to understand whether these areas flooded or not. Maybe we have also outliers, so Sentinel-1 backscatter measures that are really far away from both distribution of no-flood or flood, so we exclude also this. And also there are areas where just because we have a backscatter value that is really in the between of the two distribution, it makes us really difficult to give us with high certainty a decision. That's also something that we exclude. And yeah, so this is how it's depicted, how it looks like, let's say, these problematic areas in the scenario. Okay, next. We are at the end, that's the last slide. And I want also again to tell you that this algorithm that we will work on and begin more later, it's part of an ensemble approach that is in place at the Copernicus Emergency Management Service, the Global Flood Monitoring Service. And together with DLR and LIST, 3 algorithms are working independently, completely independently, and then they are assembled at the end. So they have an agreement decision to make a really robust, let's say, detection approach for flood monitoring. And this survey is completely open, and you can just type it online and browse it and just scrape it, the data, and it's continuously operating near real time, completely independently, and yeah, it has a global coverage. So I invite you to check it out. I guess that's it, if I'm not wrong. Next. Yeah. So if you have any questions, we are here. Otherwise, you can also save your questions for later because we will do the practical workshop later.